Okay, welcome everybody. Last lecture before the summer break. Today a little bit of a summary, not just a plain we did this and that, but putting things a bit more in perspective. With regards to industry, as I announced last time, you may see a certain gap between the things you're learning here and the things you will be seeing in industry, and that might be quite a shock. I was quite under shock when I entered industry, so I did my PhD in databases. Long time ago, and then I went to industry, and it was a shock. It was a disaster what I saw, how people did that in industry. It was just a nightmare. Yeah, and there's the exam, of course, on 29th of July. So this is also a little bit of a preparation. So I won't go into detail too much. Here and there, we will be touching concepts. Yeah. Okay, with that said, let's start. So this is the application view we used throughout this course. So there was always an application, and then there were a couple of techniques I explained along the lines. So for IMDb, it was relational model and relational algebra, and then there was actually a part 3. I put it after data journalism. It's also related to that. So from databases to the web. Yeah, so web applications, Django, and the REST API. We talked about that also in the context of IMDb. We had this NSA application topic where we talked about the basics of SQL, SQL 92 standard, the problems with joining different databases, the big data problem, and privacy concerns. So databases manage metadata, and you can do bad things with that, so be braced. We talked about countermeasures a lot in the second part of that lecture. Then we had this more technical block, not so much of an application, but more of basic query optimization. So what happens under the hood of a database system? How do you get from SQL to an executable program? Good news is you don't have to worry about that. The database system will do it itself. There's a ton of techniques. We started really easy with old techniques like rule-based optimization. I always claim in this lecture that no one uses it anymore. I'm still learning every day. No, it's not true. Many people are still using it. Many systems are using it. I actually spoke to one of the central people from the Microsoft SQL Server Optimizer at the conference 3 weeks ago, and he told me, yeah, it's rule-based. Still rule-based. I was very surprised because you don't really have to do it anymore. But they have an old optimizer, and it grew like that, and they stick to the approach. But if you start from scratch with an optimizer today, you will directly go for cost-based. I mean, there are applications for rules, but yeah, unnesting, subqueries and stuff like that. But it's more like a legacy thing, I would say. Yeah, databases to the web, I mentioned. Then data journalism, so graph data, recursion in SQL, which is, not so easy to read, right? It's with recursive stuff, not sure. So it calls for like what's called a domain-specific language. Cypher is an example for that. So it's much easier to express queries on graphical data using Cypher. And then I also showed how to do that. So the goal, how you should not do it. You should not build a separate graph database system, and then you have a ton of database systems in your backyard. Because it leads to tons of problems. How do you run queries across different database systems and stuff like that? The best solution is always to integrate functionality into one single system and then have a hybrid query language, for instance. Postgres supports that with the AGE extension, where you can have parts of your query phrased as Cypher and the other parts are phrased as standard SQL. That's the way to go, and it happens for other techniques as well. Yeah, and then we finally, for 2 weeks, we talked about concurrency control, one of the super strong features. I showed this analogy with the Mercedes A-Klasse. It's the same idea, hide complexity inside the system, make life easy for users so they don't have to fiddle around with threads and logs and stuff. Database system will do all the magic. And we just touched upon the very basic techniques here. So log-based concurrency control is the foundation for many things, and if you're interested in the core lecture, we talk about other things that are more modern, like MVCC, multi-version concurrency control. Very similar to Git, actually. You keep your database in different versions. You have people working on feature branches. You have transactions merging into main. So a lot of analogies can be drawn there. That's what we do in the core lecture. Okay, so this is the slide I used for the teaser again. And yeah, that also alludes a little bit to what we will be discussing today. So someone who had a big data engineering course or database course talking to someone who works in industry and has no clue or does some stuff he read on LinkedIn and Twitter. And that's what you see so frequently. In particular, people bullshitting about database technology and doing really, really stupid things. So today's class is organized as follows. I will use this table as an outline, and it's just the first 3 rows of that table. And I will always show some concept we learned about, entity relationship modeling, could also abbreviate it as ERM if you want, relational model, relational algebra, and so forth. And then I say what you will be seeing in the wild, and then I will make a note about something that might be interesting in that space. For instance, logical data independence is a technique no one uses, or few people use, and we didn't talk about it too much, but I will briefly again show what that means and what it implies and why that might be something that's part of a solution. So let's start with entity relationship modeling. Yeah, okay, that's the ideal world. You do an entity relationship diagram, translate it to the relational model. That's what we did, yeah. And then the relational model is translated to SQL, tables, data definition language. Actually, it's a name, create table, tra-la-la-la-la-la. That is what you would be expecting. Of course, that's not always the case. So what you see in the wild, people use databases without modeling. There's no interaction with customers. People just hack a couple of tables in the database system, or they even use another data model that something like XML or JSON, object orientation, graphs, no subschemas, no logical data independence. So all kinds of things happen. So it's you see it that people don't think about the schema, the implications, in particular when it comes to redundancies. Or what I have been trying to teach you in this class is, so the database system is not supposed to be a dump data store, a dump file system where you dump your data. The idea of the database system is really to have a single point of truth that cares about whether the data you're trying to insert makes sense. Yeah? So you can enforce all of these constraints, foreign key constraints and whatnot. And every time you change your data, the database system can check that and say, no, that's not going to work. Yeah? So it's the place to go to maintain your data, to keep your data in a clean form such that you can run queries afterwards. And if you don't model, typically the first thing you see is redundancies, discrepancies. In one table it says A, and the same information is modeled in another table saying B. So what is the truth? Is it A or B? All of these things happen. Schemas get too big. Yeah? So if you hear about SAP systems, there are these, if you talk with people working for SAP, they frequently say, oh, we have a schema of 20,000 tables. What schema in the world should have 20,000 tables? I don't see that. Yeah? So there's something going on there. That's not correct, I would claim. So schemas should have a reasonable size. If it gets too big, I would really ask some hard questions whether that makes sense. Yeah, that's about modeling. And as I said, I will show that briefly. So it's always this table. I show this table, then I point to certain techniques. Here in this case, ORM and Django we already learned about, but some we haven't learned about yet. So everything that's on the right, I will show extra slides immediately afterwards. Relational model, there's this weird discrepancy between relations and tables. Relation is a set of tuples. There's no duplicates, there's no order. Use the database system, you will see tables, there are duplicates, there's an order. People query the database without an order by and make assumptions about the order. Oh, don't do that. People do wild things with that. So I've seen so many anecdotes I could tell you. But then, similar to the modeling problem, so you add tables to your database system, you iteratively extend it over years, you add an attribute here and add a table there. Yeah, and then the schema evolves typically. It's typically like that. Oh, the developer needs to store some extra data and then hex it quickly into the database table. And then other developers see it, interpret that attribute differently, store some other things, do some other queries. All kinds of spaghetti situations will occur. So a very good recipe is typically that you have a dedicated senior developer who owns the schema, who is responsible for the schema, and all requests go through that developer. Well, you have two for that, yeah? But you should forbid at all costs to allow developers to change the schema. That's absolutely a no-go area. Every developer who wants to change the schema should have a good case for we really need to change it. No? Yeah, that's how you would do it. Yeah. And yeah, today these requests to databases are hidden under ORMs. And we talked about Django, but there are many other ORMs. So that's the wrapping from the object-oriented world to the SQL world, such that you don't have to send SQL queries anymore. Again, keep in mind the biggest effect is not that it's easier to query. The biggest effect here is you avoid SQL injection. It's the biggest risk you have as a database developer. The database can be slow, it can be crappy, it can have bugs, but if you have SQL injection, you're toast. So that's the first goal you should have in database development. No SQL injection is possible, because if you lose data you're not supposed to lose, it's not too good. Yeah, so there's many redundancies, no normalization, legacy fields. Yeah, that's another phenomenon you see in old schemas. Back in 1975, someone created the attribute. No one uses it anymore. No one knows what it is used for. The developers who created it left the company or retired. But it's still in the schema, and no one dares to remove that attribute from the table. Yeah? So usage of data so basically, yeah, a referencing scheme. Yeah, I mean, if you reverse engineer a database, it's one of the first things maybe you want to do is to check who uses which field in which semantic. Yeah? The bigger the database becomes, the more difficult this will get. Yeah, no views. We talked about views. That's a very powerful mechanism in databases to hide certain schemas. I will show that again in a moment. Or too broadly defined domains, or weirdly defined domains. For instance, for gender, you see people use as a domain string, and then M for male, and W for woman, female, and then other letters, and it's not constrained, and it's unclear what you can enter there. And some application developers enter a capital W, another a capital M, and stuff like that. So if you don't constrain that, you will get crappy data. I mean, what do you expect? So it should always be well-defined and restricted to meaningful fields. Yeah, relational algebra, that's the interesting thing here is, so as I'm said again, so there are now other libraries you can use to do data processing. For example, Pandas, which I believe has a very terrible data interface, but it allows you to operate with CSV files easily. There are other libraries. Spark has become popular in the context of the big data hype. So Spark is basically distributed relational algebra. But with Spark you can compute planet-sized data sets, create plans, write operator trees, relational algebra expressions basically, that get then optimized through rule-based, cost-based optimization, whatnot, all the techniques you learned about in this class you will see in Spark. But that's basically relational algebra plus. So it's, relational algebra is super fundamental. No matter what you do, you will be using that. Yeah. Hard-coded query plans, that's also another concern. We also did research back in, I don't know, it was around 15 years ago, there was a big wave in data research about MapReduce. Did any of you hear about MapReduce? It's a technique that was invented by Google initially, and we did some research in that regard, but we quickly found out, hey, that's a hard-coded physical execution plan, a hard-coded physical plan. Yeah? And that's exactly the opposite idea of what databases do. Opposite databases try to be flexible. Huh? You have a query, you do a logical plan, a physical plan, and depending on cardinalities and the situation, it may be a different physical plan. So if you have a system that has a hard-coded physical plan, well, that's not the best thing you can do. Yeah? But MapReduce was doing exactly that. And consequently, MapReduce was replaced by systems like Spark or Apache Flink from Germany, actually, from Berlin. Yeah, just to two slides on this physical versus logical data independence. Physical data independence in the database means that the database schema is independent of its physical realization. Changes to the physical representation of the data, hardware indexes, and whatnot have no effect on the database schema. This is in sharp contrast to assume you store your data in a binary search tree. Assume you store your data in a hash table, in a bitmap, in a file, on this iPad, on that laptop. There you're physically dependent. You're making a decision on the physical storage of your data. Also, if you make a decision to store your data in a specific file format, that's a physical decision. And the idea of database systems is to abstract over all of that stuff and say, no, we're more abstract, we're more on the logical level. Yeah, sure, eventually we have to make a decision how to store it physically, but that's the second thing, that's the second layer. So one of the strong features is we have physical data independence. You design your schema on this logical layer, and this physical stuff comes afterwards. And this has so many advantages because, in particular, for scaling a database system, it doesn't matter how big your data set is. You design a schema that reflects semantically what you're supposed to be storing in the database, but no matter how big your database becomes, you will have the same schema. The schema is not going to change, no matter whether you have 3 tuples or 3 trillion. Doesn't matter. Yeah? And that's a cool thing. So you can scale much more easily than if you hard-coded it. If you hard-code your data system against certain index structures, maybe those index structures will work for a certain size, but not for others. Yeah, then you have to revise your system and so forth and so forth. By introducing this abstraction layer, you gain so much, it's incredible. And another type of independence is logical data independence. That means the views of the end users are independent of the database schema. Changes to the database schema have no effect on the user's views. In other words, so what we are talking about is information hiding in the sense of object orientation. So this schema hides the physical stuff underneath. The user only looks at the schema. This is information hiding. And now we are adding another hiding level, so to say, okay, now what the user sees are views, these dynamic views we talked about in this lecture. And we forbid the user to access the actual database schema that creates the table stuff we're using to create a specific schema. And that has a couple of other advantages, because now you can all of a sudden change the schema without necessarily having to change the views. Yeah, if you make the decision to, on the schema, you split the tables differently, you keep all the attributes and so forth, you can just adjust the view definitions, but maybe the applications that are written against those views don't have to be changed. And that's a very strong feature, also super useful for access control and stuff, but it's hardly used. But I would really recommend taking a look at that, because it's super useful. Then for reality, that's also I wasn't aware of until like 3 or 4 years ago. I was assuming everybody uses that, but if you look at web applications, hardly anyone uses logical data independence. So typically when you have a web application, we had that here when developing with Django. Django operates on the tables. You have your models that are mapped to tables, not to views, and then you operate directly on the tables. That means you don't have logical data independence, and it's very common to do it like that. But you could also use Django with logical data independence. It's just can be awkward, but that has to do with SQL. That's another story. Normalization, I think we touched that briefly at some point. In some database courses, it's part of the curriculum, first, second, third, fourth, fifth, sixth normal form, and I forgot the intermediate forms like Boyce Codd normal form. Yeah, that's kind of interesting, it's kind of helpful, but again, normalization is not, actually you don't need this stuff. If you do an entity relationship model, you get your database in third or higher normal forms in a good quality automatically. It's nothing to worry about. So normal forms is more like for the reverse engineering. Trying to, you have a database schema that falls from the sky, you enter a company, you see, there's a database schema, and now you want to give it a grade. Is it a good schema, yes or no? And normalization is a good grading scheme. Yeah? So if you're in a reverse engineering situation, that's something you could use, but not if you design from scratch. Yeah? And it's also a bit outdated. It's really was developed in the 70s or something, tons of papers back then. And it's strongly oriented towards atomic domains. Yeah? We also touched upon that briefly. So many people say, so there's this first normal form that says what you store in an attribute value must be atomic. You're not allowed to devise it any further, to split it up any further. That means in an atomic value, if you have your table, and then you have whatever, here's attribute A, and then you store a data value here. What that means is you're not allowed to store a list or a struct or an object or table as a data value. That is what first normal form is doing. This is hopelessly outdated because it was superseded with SQL 99 already, 25 years ago. So what's the point of forcing it into first normal form if reality has advanced so much beyond that? You know? It's a contradiction. First normal form is already a contradiction to modern SQL. Yeah? So what's the point of teaching normalization? Yeah? But still, for certain scenarios, it might be a useful tool, but I don't think it belongs to an undergrad lecture. Yeah, and then the other thing you will bump into, I mean, I even have these discussions with my PhD students here and there. One of those was really religious about that, but I said, no, it's just two interpretations. And that has to do with how do you read an algebra. So this is relational algebra as we had it in one of our notebooks, directors, director genres, cross product, filter, another filter, some projection. Had that in our notebook. And it's always a question, how do you interpret something like that? Yeah? No matter whether it's a visualization like here, or the Python equivalent like there, or the Greek textual equivalent on your mini tests, there are two interpretations. The interpretation one is this is procedural code that should or must be executed exactly in that order. So you can interpret that and saying, the cross product happens first. Then there's a selection, then there's another selection, and then there's a projection. That's exactly as specified in the order. The other interpretation, number two, is this is just a special form of declarative programming. So with a relational expression, I'm just declaring how my result should look like. I'm declaring that is what I want to compute. And in that world, the database system is free to play tricks, to change the order. We had predicate pushdown, for instance, or here cross product, and this selection on top can be rewritten to a join, of course, all kinds of magic. As long as the result looks the same as the user expects it to be, you're fine. And that's the entire art of query optimization. The query, the user declares what data the user wants to have. And as you can compute it in any way, it doesn't matter. The database system can compute it anyway, as long as it's the same as what the user had in mind. With that declaration, you're fine now. So here you just have to be careful when discussing these things with other developers or researchers. Just maybe a little question, hey, what is the interpretation we're using? Is it the declarative one? Is it procedural? Just to avoid misunderstandings. So I've seen that so often. SQL, so part two of our table. That's also a very common thing. You see that people only use very simple SQL, and that only partially. And then the typical problem is that the application logic is to only read relations into the application code and then do kind of data processing in the application. Yeah, so in the Django world, that would mean you read a couple of tuples into your Python program, and then you do data processing in your Python program, even though that could have been done by the database in the first place. Yeah, so it often has to do that people don't understand that certain functionality is available, and that's a problem. And it also reinvents parts of SQL and the query optimizer, yeah, that is in the way of scaling and so forth and so forth. So, yeah, this is, did I mention that user logic horror story? I don't know. There was a cool article a couple of years ago where a manager decided to replace an old COBOL-based database system from the 60s and whatnot with a modern relational database system. And one of the senior developers, one of the COBOL experts, was asked to make the transition from COBOL to the relational database system. And they made the transition, and once the transition was done, they found out that the relational system was actually slower than the old COBOL system. And what was the problem? Naja, someone then inspected the stuff, and basically what that developer did was he created one huge table with two columns, ID and file, and all the files that were previously done in COBOL were now an attribute value in that table. So basically just used it as a file system. Yeah. Basically not much logic was needed, a change to the logic was needed, but it basically used it as a file system to store whatever large files here in a single table in the relational system. But if you do it like that, of course, you're abusing the database system as a file storage, but don't leverage all the query processing capabilities. So, I have a link to that somewhere. It's quite, yeah. Then data economy. So the idea to only store as little data as possible. Here we see the opposite, in particular on the web these days. Mostly it's not followed, but it's really easy. Just sit down, hey, do I need this attribute value? Do I need that information? Is that really required to implement my application? Yes or no? It's so easy. Yeah, then ACID. So the ACID properties, often this is only used per tuple, in particular if you ever bump into key value stores or NoSQL systems that typically have ACID only on a single tuple. Yeah, the strong feature of a database system is that we can do transactions across any number of tuples, across any number of relations. Yeah, so we have real transactions. Key value stores often don't have it. Then consistency, as I said before, the database system has a ton of tools to ensure consistency, to make sure that whatever change you want to do corresponds to your semantics of the data. It's an endless system, so many things you can do. So one keyword there is triggers, or on Postgres, it's a rule system. So basically what that means is you can define rules that have to be fulfilled, arbitrary constraints, and can check that automatically. Isolation, we already talked about the issues and the differences of database systems. You have all kinds of relaxations in the real world. One is eventual consistency. I have a slide on that. Key value stores, I have more slides on. Okay, we will go into detail in a moment. Huh? And then durability is, I mean, as I said, durability can only be fulfilled if you can guarantee that the change is never lost. You cannot guarantee that. Think about the Star Wars Death Star example. Yeah, if you lose all your replicas, you're toast. Yeah? The data is gone. So you can't reach perfect durability, but you can try that the likelihood that you keep some data goes close to 100%. But you can never reach 100%. That's impossible. Okay. So in more detail to what I just said, so implementing functionality. So when you have your stack, and we talked about that several times in this lecture, of hardware, operating system, database, application server, and front end, and of course it can be much more complex, and you want to filter some data. There are several options where you can filter the data. Yeah? So you could send all the data to the user, and then the user browses through the data and filters it. That's one option. The other is you send it to the front end, and then the front end filters the data. That's also an option. Or you filter it in the application server, or you filter it in the database system. Or maybe you filter it already on the hardware. How would that work? So there's a clear trade-off here. If you have a large data set and you want to filter it with a certain predicate, for instance, you should filter as early as possible. That's again a variant of predicate pushdown. Yeah? What do you gain? You have to ship less data to the user. It may also be that you improve the overall end-to-end time. For instance, the front end, depending how that works, maybe it's JavaScript, probably much slower than some native binary code in the database system. So that might be much slower. Yeah? So the idea, whenever possible, is to push down functionality as much down as possible, predicate push down. And for this course, this means whenever possible, try to do the heavy lifting, like filtering on the database already. Yeah? Because that will improve your overall user experience dramatically. There are also techniques. There are different processing in memory, that's the name. I'm sure whether I mentioned it in this course, processing in memory techniques allowing you to filter directly on the hardware. Yeah, that's even better because in this world, even though the database has very good algorithms, it still has to maybe access and read all the data from the hardware if there's no suitable index available. Yeah? So that is still a lot of work. So there's there are special types of storage media allowing you to filter on the hardware. There's, for instance, RAM variants, DRAM variants, allowing you to execute simple filters on hardware already. It also exists for SSDs, where you can do simple operations on the SSD already with the goal to send less data up to the OS and the database system. Yeah? But that's not the first thing to look at. For you, it's important, whenever possible, try to execute stuff on the database system. Yeah, that's again what I just said. Yeah, here another example, it's not only for performance, is where to implement transaction logic. That's also something I've seen, that people reinvent transactions on the application server, and that's something you should avoid at all costs. I mean, all this machinery is already in the database system, so please delegate transaction processing to the database system. Don't reinvent that yourself. That's not going to fly. Key value stores, that's also a weird topic actually. So what do? They allow for the efficient storage and retrieval of keys mapped to arbitrary values. Key is mapped to an arbitrary value. Transactions over multiple keys are typically not supported, so you can only fiddle or have a transactional semantic on a specific key value mapping, but not multiple of them. Now, if you think about the accounts example we had for transactions, when we do a money transfer from one account to another, that's 2 keys, 2 account numbers that are being manipulated, but this is only one. So a transaction for money transfer doesn't work typically in the key value store. And functionality inquiries that cannot be mapped to the key value semantics are usually insufficiently supported. So historically, what happened is people stood up and say, databases are bad, we need key value stores, they scale so well. And then later on, they kept on reinventing and adding relational database technology, which was kind of funny to watch. So the big advantage key value stores have sometimes is scalability across different machines. If you want to have a data storage system that scales beyond a single cluster, can be tough with a relational database system. This is much easier to achieve. A web scale, caching frameworks, Google-style applications, that's a place where key value stores have a case, but for many others they don't. The interesting thing is, what can you map to a key and value? Yeah? And the answer is anything. So what is a key value store? I mean, the internet is a key value store, let's face it. So the URL is mapped to the content of a website. Yeah? You enter the key in your browser, and that gives you the value, which is the content, HTML and whatnot, being displayed by your browser. So the internet is a key value store, if you wish. A hierarchical file path, that's one of my favorite example. So file systems have developed in a different community, in the systems community. But if you think about that, I mean, this is a key value store. The key is the hierarchical path you have in your file system. Yeah? So the key is really something like whatever, home, whatever, lectures, whatever, BDE, whatever, 12, no, today's like 11 or something, whatever, 11.pdf. This thing is a key. It's a hierarchical key concept, but who cares? Hey, come on, it's a string. I don't care. And the value of that, well, that's the contents of the PDF. It's a key value store. Yeah? And if people had done that from the start, I mean, it's always easy to say afterwards, we should have done it from the start, but even if you talk to file systems people today, they say, yeah, it's a key value store, let's face it. So it would be a much better idea to start with a key value store or even with a database system that can do the file system stuff. There are actually proposals in that regard. Same holds for ID to JSON. Yeah, so a variant of that is called document stores, and the only thing that's being changed is that the value is of type JSON. And that's called a document. MongoDB became very popular with that approach. Yeah, so they are very efficient and sufficient if no other access patterns are needed. So if the only thing you need is looking up by key, then it could be good. The scale-out properties are very good of many of these products, but the use case is very limited, and it's super slow for queries that do not query via the key. So if you have another condition that's not mapped by the key, if, for instance, I don't know, what was the example? Yeah, if you're looking for whatever certain keywords in your documents, you're toast. Yeah, you don't have that search capability. You only have efficient search via the key in those systems. And basically, it's nothing but a distributed hash map or index. So if you write that in a relational database system, yeah, you could also simply do a relation with two attributes. You make key the primary key, that attribute key, and attribute value. That's the key value store. It's nothing but that. Here, if you make that a key and then you create an index, you have very similar capabilities. Actually, a long time ago, we did an experimental study on that, and it was surprising to see how fast databases are. But again, key value store, if you really want to scale out, may have a case. Yeah, oh, too slow, too many slides. Okay, then rules and triggers. So that is the idea that you can use to provide consistency in your database. It's based on this ECA pattern, ECA meaning event, condition, action. So you're looking for specific events. An event occurs, something happens, and then you check whether this event fulfills a specific condition, and if that is the case, you perform a specific action. That's called ECA, and also used by so-called database triggers. And those are ECA rules that you can formulate directly in the database system. You could also do that in Python. There's, for instance, in Django, there's an event mechanism that does something very similar. And maybe that's a good thinking exercise. So what I'm trying to tell you is, you have your DBMS that has these ECA rules. Again, this is a question, where do you implement which functionality? It's the same, it's an instance of that again. Operating system and whatnot, yada, yada, yada. But here's Django. And you could also implement your ECA rules here. So what is the pros and cons of these two approaches? Anyone has an idea? Two options, right? Could implement it in Django with Python or in SQL, the database with SQL trigger semantics. What could be pros, what could be cons of something like that? So this is your Django app, number 1. And maybe there's another Django app. Number 2. Operating on the same database. What is the difference here? Yeah? Yeah, is that, are you raising your hand?
It could be the case that in case of DBMS, we operate on those. So in order to identify those events, we have to perform some operations. In Django, maybe it's optimized to a certain level, and that's why we identify them quickly. But then we have to also pass some data above, more data. So that would be the con of that, and so would be
yeah, that's true. I mean, the filtering trade-off I showed before, that still exists here. Yeah, that's the same trade-off. Yeah, if it's a filter operation and maybe the trigger, what was it? Here, yeah, this slide. That's kind of the same trade-off. How much data do you send around, efficiency, tra-la-la-la-la. Let's ignore that for the moment. Let's ignore whether that is efficient or not. Triggers can actually be pretty inefficient. Anyway, so just in a situation like that, you have two applications that are run this, on the same database in the same database management system. So operate on the same schema, the same data. And then you have option 1 is you implement these rules in the database system. Option 2 is you implement it in one of the applications. What is the difference? Yeah?
The difference is probably that if you do it at DBMS, we can also use the ECA rules on different Django apps.
Exactly, that is the difference. You do it once and for all where it belongs. And it belongs to the database system. No matter how many applications are using that database, you solve that. You make sure that these integrity, all these constraints, the consistency, the C, is fulfilled once and for all, no matter how many applications are using that. Yeah? Here, this is only checked for this specific application. Yeah? So that's option 2 is actually this. Yeah? So if you go through application 1, you check the rules and avoid these problems. If you go through application 2, there's no ECA, the DBMS doesn't have it, so you can insert any crap there. Yeah, so it makes a lot of sense to have these consistency rules very close to the data, which means inside the database management system. Yeah? And that's the problem there. Yeah? Also, you only have to implement it once. Yeah? You could then argue, yeah, but I only have one application. Yeah, so I will never add a second application. Yeah, sure, yeah. Real life is different. Yeah, you start with something and then users come in, yeah, we want to do a second application, you know, and then, then you have the problem. Yeah? So I would start with something like that if possible. The downside is ECA in a database system. Not so easy to use. Right? Yeah.
Right? How can you filter stuff before it even exists?
Yeah, then the hardware has to offer an API, of course, where you, for instance, push down a predicate or something like that. So the standard, so hardware typically has a block level interface where the operating system says, oh, give me block 42, and then you get like 4 kilobytes of data, and you can do something of that with that. That interface is not enough, obviously. You have to invent a filtering mechanism. You have to have a possibility allowing the database system to push down a predicate to the hardware, such that the hardware understands the stuff. Yeah? And once you do that, the hardware can do the filtering and send up only the qualifying rows.
Because the data is stored on the hardware.
Yeah, of course. It's always stored on the hardware, DRAM, SSDs, and whatnot. That's hardware. CPU, storage, medium, and whatnot. That's the hardware. Whatever you do, it's on the hardware, right? And you have to push it up in the stack. So here's an example for such a rule. I would implement that, and that's what I mean by maybe not so easy to use, but can be very powerful. So maybe a good practical tip would be, maybe you don't want to implement each and every rule here, but maybe the most important ones. You could at least try to do something like that. And this is how it looks like. Yeah? Create trigger with a name. Then you say when that is about to be executed, which is after an update on accounts. After an update on the accounts relation, then what is to be done for each row. You check whether the old entry is distinct from the new. You execute a certain function. Yeah? So this is basically the definition of the condition, the event and the condition, and then the action here is here to execute the function. So this, for instance, is a function that logs updates. Yeah, so you could keep a log of the changes done to that specific table for legal reasons, and that's a good idea. Yeah? So if you want to really trace who changed what, who changed the account balances, then that's something that's absolutely useful. Yeah? And there's a video in German, if you're interested, that explains that in more detail. Yeah. Part 3, security, privacy. Security, again, that's something you should design from the beginning. It's not an afterthought. Security, when you start implementing a system, when you start designing a system, security must already be part of that. It's not that after 2 years you start thinking about security. That's not how that works. But in practice, you see all kinds of things. Same for privacy, that is in the wild sometimes considered an afterthought. That's not how it should be done. Then quality assurance, the so-called staging environment, I will explain in a moment. Then this application testing versus consistency of the database. Yeah, that's again the trigger topic. How do you make sure that your database is consistent? Documentation might be missing or maybe meaningless. Maybe it's unclear what the user roles are. The semantics may be unclear. That should be written down clearly for people to make sure that that's our common understanding. Extensibility could be difficult due to missing interfaces. Unknown dependencies in the code is a huge issue for existing systems. And again, here, logical data independence may be a good tool to use. Then for physical design, that's also sometimes not so clear to database users what's possible. Many cool things you can do with that. I will show that in a moment. So did you see, or do you know what a deployment environment staging thing is, kind of? Yeah, that's a standard architecture you use in development to ship code to a production server. So at the end of the day, you have a production server. So that's a system actually running your database with the customer data. Yeah? That's called production or prod for short. Yeah, and then you have a system where you develop your stuff. And it's not such a great idea. You develop something and directly copy it, aka push it to production. That may break a couple of things. Huh? So I heard that from one of the employees who works at a German bank, when we talked about these scenarios where the banks crashed and they had a hard time to recover their systems. What happened? Yeah, they did a major change in their production server. Fiddling with bank account numbers, which completely blew up everything and screwed their system. Very hard to recover. That's not what you should do. So a typical environment It's also called the CI pipeline. Sometimes it's also then integrated with GitLab and CI and whatnot. But in terms of systems, just talking about the systems, you have 3 or 4 different systems. And one is, a development system could be a laptop where you can also run tests, local tests, unit tests, Playwright and whatnot. Then there's typically an extra test system that's also used by your CI to understand whether you fulfill certain tests. Those may be short-running tests that are executed immediately. There may be nightly tests that are much more demanding and run overnight. But there are test systems checking whether the modifications you did make sense or create any bugs. And then there's staging that is super useful. That's basically a copy of production with production data. So you can use a staging system that has the latest code. The users are not seeing this code, but you can try out your code with production data, which is super, super useful. So we're using that in our master application system heavily. Why do you need staging if you have unit tests? You have unit tests, you can ship to production. So what's the point of staging? Yeah?
The load might be completely different,
The load, maybe you see some lagging, maybe the user interface is slow, maybe you did something that looks fine on your test data, but it's really slow and not working on production data because the size is different. Then you might actually think about performance tests. That's another big issue. You could also integrate into your test system scalability tests, telling you, okay, for this fake data, how big can it become until it breaks? Something you could do in the production environment. But you're totally right. There's something you could discover in staging. What else could be the reason? You have tests. What's the point of having an extra staging server? Yeah? Exactly. If you make the assumption that your tests are perfect, then you're doing something wrong. A test typically overlook things. We learned that the hardware we had very good test suites in our system, but then we had real users entering, and oh my gosh, what happened there? Really weird things happened, and you only see that with production data. Then you ship your feature to staging, make sure the production data is up to date. You try out certain things, try certain tests, try to do certain things in the system and say, oh, that's going to break. And then you have to fix your code. And that's also an opportunity to add more tests. The tests you overlooked, basically. It's kind of a unit test detection system you're building with something like that. Super useful. So I can highly recommend doing that. So it's also sometimes called a replica. So replicating the data from production to a system where you can play with new features. Many companies do it like that, and that's the way to go. Physical design advisory and performance tuning. So physical data independence is great, but at some point you have to define and configure how the data is stored physically, indexes, how many machines, which hardware, data distribution, and so forth. This is typically a dedicated role. In particular, for bigger database systems, that's called the database administrator, or DBA. However, depending on the system you're using, you have tools that help you with that. And they're called physical design advisory. So that's a tool for semi-automatically setting the physical configuration of a database. For instance, these tools may recommend to create certain index structures. They say, oh, you should better create an index there. Or they say, hey, you better partition your table, or you better, whatever, get some second server and distribute the load somehow. And this sometimes goes as far to approaches like auto-tuning, which is now, unfortunately, was shut down, the project. This was done by a colleague from Carnegie Mellon University. Had some nice ideas in that space. So that the idea is that the database system configures itself automatically. There are also many AI, machine learning, and whatnot approaches. So you can do many things doing there. Here's an example from Microsoft explaining how that works. And that's a super useful tool. Yeah? So you don't have to find that out yourself, but yeah, the machine can do that. Yeah. Also, this will go faster. I'm really heavily running out of time here. Sorry. Okay, part 4. Data management, or in particular specific systems. You see in the wild that the IT diagram, how systems are split in the company, is often aligned with the organizational hierarchy. So every department has its own server, its own database system, its own mini IT infrastructure. So if you look at the organizational hierarchy, you often learn a lot about IT as well. There are all these social aspects you see, yeah, power games you see in companies, so that people are not necessarily interested in building the best product, but making a career. Yeah, these things happen, of course. Data may be distributed across different systems, even though it doesn't make sense, but just for this ownership argument, that certain people want to own their data. They sit on their database system, and they don't want others to have access to the data. And then you see things like query processing happening along organizational hierarchies. You know? And then you end up with data integration problems. Data integration problems meaning, yeah, you can't send the query to one database system, but you actually have to get the data from 5 different database systems and somehow split up the query and stuff like that, and things will get more complex. Yeah, then there are other social issues or psychological issues, let's phrase it like that. What you see too often is the perceived knowledge of employees, or sometimes even an active concealment or ignorance of one's own lack of knowledge. So what that means is, I think a super strong feature you should try to develop is, no matter what field you will be working on is to understand what you're good at and what you're not good at. To a very detailed level, understand I'm good at this, but I'm not so good at that. And of course, when you're in a company situation, it's typically also competitive. People want to impress their manager. They will never say, yeah, I didn't understand that. You won't hear that sentence in the company. They will try to fake something. They will conceal that they didn't understand a certain thing, or they will maybe sometimes conceal that they're lacking knowledge in a specific area. All these social effects for good reason. Yeah? People don't want to lose their jobs. They don't want to climb down the hierarchy ladder in the company. But this is a problem in a team. It's a huge problem if people claim they can do something and they cannot. And then these people are in charge of certain things, but yeah, do stupid things. It's a big problem. And I can only recommend to you, at least for yourself, how much you tell others about that, but for yourself, you should have a very good understanding what you're good at and what not. It's so helpful. I know in my area, in computer science and databases, I know exactly what I'm really good at and what I'm not so good at. And then, of course, I focus on the stuff where I'm good at, because the others, there are other people who are much better there. So what's the point? It helps a lot also in guiding what to work on and so forth. Yeah, then this conceptual thing, I have many slides on that. I will explain that in a moment. And also buzzwords, that's a huge problem in industry. That certain terms are invented that are very vaguely defined, but for that I have tons of slides. So let's play some buzzword bullshit bingo, and that has to do with ambiguous communication you see in industry. And I'm using, of course, big data as a term. So that was a buzzword invented, I don't know, 10, 15 years ago, and it has some typical properties of a buzzword, and that is, if I write it on this slide, or if I say it, big data, this is just a symbol pointing to a specific meaning. Yeah? So language people split that up very well. So if you have such term, big data, it may mean many different things. Maybe it means large data. Maybe it means 4 V's. I'm not sure whether you heard that definition. Doesn't matter what it is, but that's something people try to define what big data means and ended up with something that's called 4 V's. Maybe it could mean NSA for you, in particular for laymen, when Snowden came up in 2013, there was like equality. Big data, that's NSA and master surveillance. Yeah, I don't know. Yeah, that's one interpretation. Or it may mean Spark or MapReduce or NoSQL or whatnot. Huh? And that's a problem. So it's not clear how it is defined, because if you're in a conversation with someone else, so person one says big data and the other person hears big data, that person may have a different interpretation of what big data actually means. Yeah, so that person may have the interpretation, yeah, big data for me actually means MapReduce. Yeah? However, if for this person, big data means large data, and for that person, big data means MapReduce, then you have a translation error. Yeah? So from left to right, intended meaning was large data, got translated to MapReduce. So all kinds of confusions happened there. Yeah? So large data was in the brain of that person, and that got translated to MapReduce. And that's a problem. That's a problem in any discussion, be it in engineering or in particular in research. It's a super big problem. And clear communication is more like something like that. And now I'm using a term we learned about, relational algebra. There's exactly one interpretation, I would claim. I mean, you could argue whether that's a relational algebra that has maybe some other operators, some extended operators or not. But relational algebra has a join operator, selection, projection, tra-la-la-la. It's super clear what is meant. If I say relational algebra, you understand, relational algebra, these operator symbols, stuff, Greek, whatnot, right? So if you're in a room with someone who had a database course, he or she will understand, it's relational algebra. So there's no translation error. Relational algebra in that brain got translated to a relational algebra in that brain. Yeah? And with that, you can draw a buzzword bullshit bingo landscape. So what I'm depicting here on the x-axis is the number of interpretations, the number of meanings for a specific term. Yeah? So here on the left is stuff we learned about in this class. And all of them are well defined. It's clear. If you learned about them in this class, you know what they mean. The further you go out to the right, the less clear it becomes what it means. Huh? For instance, large data. What the heck is large? Large with respect to what? Machine learning can mean so many things. Or these days, it's AI. AI equals large language model. Now you ask Jörg Hoffmann, AI equals automatic planning. You ask someone else, equals machine learning, equals robots, Terminator, whatnot. Yeah? So my recommendation is if you work in an engineering team on research, you should only use terms on the left, terms that are well defined. If you want to get venture capital funding for your company, you must use the terms on the right. That's very important, because with that you will get the funding. If you go to a venture capitalist and say, I want to do this fancy predicate push down on the relational model, combining data layouts with cost-based optimization, good luck with that one. Yeah? But if you say, I have this new fancy AI blockchain NoSQL method operating on big data, where do I sign, right? Yeah. So that's how the world works. Yeah? And another recommendation in that regard is really, if you are in a discussion, I do that every time with my PhD students, and particularly in the beginning when people start, also with master and bachelor thesis students. If there's a term in the room where you sense, is it clear what we're talking about? I say, stop. And then I ask, okay, what do you mean by term X? What is your understanding of term X? Yeah, then we clarify that, make a definition, and then we continue talking. And that makes your discussion so much more efficient. It's unbelievable. Yeah? As soon as you're piling up terms that are not clearly defined, your discussion will go nowhere. If you ever attended, try to attend a discussion of IT managers. Yeah? They will discuss in that space. And nothing good can come out of that typically. It's very unlikely. Yeah, but you should try to discuss in this space. It makes such a difference in terms of efficiency and mutual understanding. Yeah, there's also maybe another anecdote because I think it's so important. The last days I had a couple of discussions with a colleague from the US, database professor, and it was super eye-opening to see, even for terms that I put on the left. Yeah, I said, no, there's no ambiguity whatsoever. So I learned, no, there are terms that are ambiguous and are used differently in different sub-communities of databases. So database research is a very big community with thousands of people. It has sub-communities, and that guy is from another sub-community. And one of the terms, not here, but a term that I believe is clearly defined, no, he uses it differently. And it became clear very early on in the discussion. I said, okay, you use it differently, right? I mean, what is your interpretation? That's your, cool, that's how I can see it. Oh, interesting. Yeah? So it's very eye-opening also to see these things, yeah? And synchronize yourself with other people. Yeah? Okay, and the other wild thing happening in industry is concept versus technology. Now that's the problem number 2. That's a confusion of design dimensions. So there are different dimensions. So one we learned about so far is these fancy sounding buzzwords. Yeah? Labels and terms that don't mean anything. That's dimension number 1. Then there's dimension number 2, that's technical principles, yeah? The things that are clearly defined, and I just mentioned relational model, algebra, and whatnot. But there's a third dimension. Maybe I can skip over a couple of slides here. There's a third dimension, that's software platforms or concrete implementations of frameworks. For instance, PostgreSQL is a concrete database management system. Spark is a concrete implementation of relational algebras, such as Flink. Yeah? MongoDB is one implementation, one specific technique you can download and use of a key value store, and so forth. So these are concrete software platforms. Yeah, and then you have these three-dimensional space. And what you see often in industry, which is super wild, is that people design solutions in this dimension. Yeah? So they don't say, oh yeah, I have to first create a schema and then relations and define integrity constraints and think about which queries and which views to define. No. They say, okay, I need to install Postgres or Spark, and then I connect that on my server using whatever technology and do whatever technology on top, this Python library, this C++ stuff, whatnot. So it's already overfit to a specific technology. Yeah, the technology is not designed independent from its realization, and that's a big mistake. Yeah? As a good computer scientist, you should only design here. That is your home base. The principles and patterns you learned about independent from their concrete realization. You shouldn't think in Python. You should think in an object-oriented way. That's okay. Yeah? You shouldn't think in C++. You should think in an object-oriented way. Later on, you can translate your conceptual stuff to C++, and that has extra challenges. Okay, yeah, but that's not how you start. You should always start with dimension 2, yeah, and then there's a point where you have to translate it to one specific realization in dimension 3. That's fine, but if you start here, yeah, that's really a bad idea. Yeah, and I am always happy to explain this scenario. That is a large web application I heard from somewhere in some small Bundesland, somewhere in Germany at some university. So it was a large web application with a terribly slow performance, minutes instead of milliseconds. It was basically unusable. And there was a performance problem that was like a factor 10,000 off. A factor 10,000 off and more slower than it should be. An SAP system with about 100,000 tables. And apparently no or hardly any views. And completely ridiculous performance numbers. So at the time I made this comparison, assume an ICE train, a high-speed train that doesn't run 200 kilometers an hour, but 20, I think the number is 200 kilometers by 1,000 is 200 meters times, yeah, 20. Yeah? It's like a high-speed train running at 20 meters an hour. not so great. So that just to put that in perspective, what factor 10,000 means, this obviously was completely wrong. And the solution space in that is, you profile. You could, in such a web stack, you could profile the runtime of the application, where there's the runtime of the database query. In other words, you first have to find out what is the culprit, what's going on here, where do I lose all of that performance? Is it the hardware, the application, is it the UI, is it network, whatnot? You have to profile, you have to find out, you have to investigate what's going on. That's very important. You could, for instance, run your database queries on the systems with and without load. You have to understand, is the problem is that there are so many users, or do I already see this poor performance when there's a single user? If you already see it with a single user, then then you really have a problem. Maybe your queries are really bad. What's going on? And so there's so many things you can do there to investigate that. It had more than 30,000 users at the time. And solution space, there are many things you can do there actually. Load distribution could be clarified after having ruled out that it's not the individual queries. You can split up the application server and the database. It's a common design thing. No one forces you to run Django and the database on the same server. You can split that up, could already help. You can do a performance monitoring. That's something you do in modern applications, that you have all kinds of monitors, not only for bugs, but also for performance issues that occur. If a certain view, a certain Django view doesn't return within whatever 1 second, you trigger an alarm, for instance. It's an easy thing to do, and so forth and so forth. But maybe a little bit to the setup, which was really weird, was the project setup was like 3 companies involved in the development, each with several managers, project leaders, sub-project leaders, and developers. And they had very different database knowledge. Everything from very good, the database admin was pretty good, to individual managers, which had just transitioned from other disciplines. Many physicists, chemistry, and so forth, no real computer scientists. That was really wild. And then what happened was, we have a performance problem, and everyone was pointing at each other, saying, no, it's not us, it's the other. And then the other said, no, it's not us, it's the other, without having any evidence for that. Just claiming to be on the safe side, no, it's not us, it must be the others. But they didn't have any evidence to prove that, which was super wild. So, that was a bit shocking to watch also, factoring in how much money was put into that project. And there was several performance problems combined, and longer story. But this was really pointing towards, hey, there are very simple things you could do with some minimal knowledge of computer science. You could have identified the root cause and fixed the problem. Why didn't that happen? And it had to do with people didn't have the right education actually here. So in general, independent from the problem, you will see in the wild very often the following things. So you unfortunately often see database systems used by people who don't have a clue. And I don't mean you with that. Now you have a clue attending this course, of course. But if it's more like people, we install the database and create some tables and do a bunch of wild things, maybe that's a bit clueless. And the problem, the social problem you also see then is what I mentioned before, that this is sometimes combined with people, then they believe they have a clue. They don't have a clue, but they pretend, or they actually believe, I'm a great database guy, I understand what's going on. And that's a very problematic combination. And that may come with resistance to advice, and then it gets really unpleasant. And these things lead to a variety of performance problems, security issues, architectural mistakes, and enormously high costs. And as I said before, if your role, or you should really focus on understanding what you're good at, I also claim that the manager should be good at that. So if you're managing a team later on, you should really be don't force people into certain tasks. Try to understand what they're good at, what the strengths are. Maybe you can build upon those strengths. I mean, that's the art of a great team, actually, to understand, oh, he's good at that, she's very good at that, and then they complement each other and bring in their strengths and stuff like that. And that's something a manager must understand. And if the manager doesn't understand that, he's or she's not the right manager. But here it plays an important role. If you have people, that too many people that don't contribute, that's a problem. And I always find it very shocking to see these things happening or projects being set up like that. If you think about medical domains, or for instance, I mean, would you let yourself be operated by someone who actually trained as a butcher? Yeah, I mean, that's kind of the equivalent of people you see there. You see people who learned something, then they took a 2 or 3 months programming course, and then they build systems like that. I mean, what do you expect as an outcome? Yeah, I mean, that will go wrong, I understand, yeah. But that unfortunately happens a lot in IT, yeah. So I'm really a strong, I have a very strong opinion on that people who do systems, who build software, should have a very, very strong education to know what they're doing. Yeah, so you should ensure that those who use the tool understand that tool. Yeah, and my advice a bit more pointedly is if you are managed by someone who only has business knowledge but no technical knowledge, then run, because it's not going to fly, the project. It's not going to work. I think in computer science, it's super important that managers have technical skills and maybe get their hands dirty to program as well. I also program in our project. Okay, so summary. When it comes to using database technology in IT projects, there can be quite a discrepancy between what should be done and what is done. How to cope with that? If you have to deal with database technology, be careful about the pitfalls. And we talked about many of those in the concurrency control lecture, in the NSA lecture, privacy, security, whatnot. Also in query optimizations, the performance pitfalls. And today, many situations that may occur. The interesting thing is with most of the perceived database problems with web applications can be solved relatively easily. Yeah, so you sometimes hear people complaining, oh, my database is slow. No, it's typically that it is misconfigured or used in the wrong way. That holds for most, if not all, performance problems. Finding a scenario where the database is really too slow is hard these days. Databases are super fast, they're just used in the wrong way, and that's a culprit. Be extra careful when it comes to security and privacy risk issues. That's one of the most dangerous pitfalls these days. And if in doubt, ask an expert, not a wannabe expert. That's also a recommendation for, in general, in teams. Yeah. Adding to what I just said, if you understand you're good at something, you will hit boundaries. So all of a sudden you do research, you develop something, and then you find, oh, I'm now entering space where I'm not so good at. Then you should quickly ask someone who is good at that and not try for yourself for days and days and days and maybe on the wrong track and reinvent the wheel and stuff like that. That's really the art of a good developer, to understand where they're good at, and then if in doubt, ask early. Ask early, because it can be so eye-opening and increase your performance dramatically. Yeah? That's really important. Yeah, that's it for the lecture. Just a little bit about the next iteration, summer. We will look for tutors at some point. If you're interested, those are our criteria. At least a 1.7 you should have in the final exam. Have a talent for explaining technical content, or be interested in learning more about tutoring and explaining, and you would like to join our team, then apply directly to me. Just send me an email, but wait for the final exam, of course. The content will not differ significantly, so we typically at most replace 1 or 2 weeks. But it's not decided yet what to replace. So whatever we will replace, it's not a problem for you. You will catch up easily. Yeah? So you know the material we will be using next week. And tasks will be giving a tutorial, of course, participating in the weekly team meetings, Co-conception of exercises, well, yeah, depends. Actually, we have also the rule of, supervision tutors who typically focus on conception of exercises. Yeah, so if you're a first-time tutor, you typically don't do that, but depends on how we split that up. Correction of exercises and exams. Exercises, well, not so much. We will stick with the mini-test model, so it's more like correction of mini-tests, of course, and exams, and maybe this project interviews. Yeah, then there's the next level to this lecture is a core lecture. It's probably only happening next year in winter. Not clear yet, but that's how I see it now. And there we go a little, not a little, a lot beyond the material we had here. So it's really like what you see in Postgres. It's more like a modern jet plane. But what databases can do, if you want, is more like a flying saucer kind of performance. So we look at things like how does an aircraft turbine work in detail? How do we fly at 100 times the speed of light? Are there wormholes and how do we fly through them? How can we guarantee the safety of the passengers, even in the event of a crash in a wormhole? How do we build a distributed database system the size of the planet, a galaxy, or the universe? So all things that are super relevant to your future career, of course. I'm just kidding, but yeah, I think there's a lot of interesting technology actually out there I couldn't show in this lecture. Yeah, with that, I hope you enjoyed the lecture and learned useful things for your career. If you end up, yeah, that's, I'm asking every time, if you end up working with databases somehow at some point, feel free to drop me a line and tell me about your positive and negative experiences, be it, oh, Professor Dittrich, you should actually re-add normalization theory to your course because it's so important. Yeah, maybe, okay. Or if you want to write me, oh yeah, it's even much worse than all the horror stories you told in your lecture, and here's another one. I would be happy to integrate that into my slides. Yeah. Or if it's like, oh, you completely exaggerated, everyone is so proficient in databases, why are you teaching this stuff anyway, right? Everyone knows about it. Maybe, yeah, I would be really interested in learning more about these stories from industry. And yeah, with that, thanks everybody. Good luck for the exam. Maybe see you in some other course. Thanks.